So, welcome everybody here and somewhere in the cloud, I guess. So, 100 years ago, Marston published a paper called Relations Between the Critical Points of a Real Function of N Independent Variables, which was published in the Transactions of American Mathematical Society. And what it started is now called Morse theory and can be regarded as one of the great mathematical achievements of the 20th century. So it's a foundational breakthrough in differential topology, and it gives methods and insights which have been used in fields of geometry, topology, and theoretical physics. Now, in 1988, Raoul Bott, who was sort of a great practitioner of Morse theory, wrote a survey called Morse Theory Indomitable, and where he gave sort of a chronology of the achievements. So starting with Morse, then came Thom, Smale, Witten, and Fleur. And the two talks which we have here in Simonyi look at the Morse theory most of the time after the contributions by Fleur, who opened actually the door to do many, many more type of problems. And we have two leading contributors to this development, then Cristofaro-Gardiner and Stefandini. At 5 o'clock, we will have a public lecture given by Etienne Gis, also in the audience. And you will see a master class in engaging the general public. No pressure, of course. So something I think is actually very important in this world climate we have currently concerning science. So it's a great pleasure to introduce, to give then Cristofaro-Gardiner the floor, and he will talk about from Morse homology to symplectic Weyl laws.
Okay. Well, thank you very much for that very kind introduction, and thanks very much for the invitation to be here. It's a huge pleasure. Just a couple administrative remarks before I start. First of all, I'd like this talk to be accessible to a general institute level audience. There's many specialists here in symplectic topology, but many who are not. Anyways, so things are written at a fairly high level overview, but there are plenty of opportunities to drill down with more detail. So if you want more detail, just ask at any point in the talk. Also, if you want to follow along the slides, they're on my personal website if you just click around. So if you miss a slide or something and want to just go back and look at it. Okay, so let me get started here. So we're motivated in this talk by Weyl's law. I have a picture of Weyl. It's fantastic to speak on this at the Institute because he was the faculty member here from 1933 to 1955. And let me remind you of the statement of his famous law. I have a bounded domain. I can look at the number of Laplace eigenvalues, not more than t, count them with multiplicity. And Weyl showed in 1911 that I recover the volume of the domain up to a constant that can be computed in the asymptotic limit. And this was an extremely influential result. It was conjectured by Sommerfeld and Lorenz based on ideas in the theory of sound from 1887. So it's of course a great pleasure to be speaking about this topic here at IS. And well, so today I want to tell you about some symplectic analogs of Weyl's law. In some sense, this is still a developing story. I mean, at the very end, I have some open questions, and we do know some symplectic analogs, so but we'd certainly like to know more. So we'll talk about that a little bit at the end, and I want to illustrate their value. So more specifically, I'm going to start with some general context for, one question that maybe we still don't completely know the answer to is why should there be Weyl laws in symplectic geometry? And part one will give you some context for why you might expect maybe that there should be. Then I'm actually going to state one for you. There's several that we have, but maybe the most accessible one is the Weyl law for the ECH spectrum. So we're gonna talk about that. And then I'm going to explain to you how to actually define this ECH spectrum using ideas pioneered by Morse 100 years ago. Then, like I said, I want to illustrate why this is useful beyond just its intrinsic beauty. So I want to give an application to Smail's 10th problem, namely the closing lemma. Then I'll give you a few words about how you actually can prove some of these laws. This will also be rather high level. And then I'll talk about some more Weyl laws, briefly state some open questions, and I want to advertise Soban's talk at 2 p.m. We tried to sync our talks so that they're somewhat of a continuation. So Soban's talk will give some very beautiful applications of some of these Weyl laws. So as you can see, we have a lot on our plate, so we should get started. But on the other hand, as I said, things sort of are presented at a rather high level. But please stop me at any time, especially if you want me to go back. And as I said, if you want me to give more detail about something, please let me know. Okay, so I wanted to give you some context. And for me, actually, getting interested in this, I got interested in this subject through the theory of symplectic ball packing. So I want to pitch it to you this way. Quite closely related is the idea of a symplectic size measurement. So maybe I should start by telling you what a symplectic manifold is. Well, I'm talking about a 2n-dimensional manifold. It has a closed 2 form. It wedges to the volume form. I think maybe we've all seen this before. But anyways, these are the natural setting for classical mechanics, and so they're of fundamental importance. And a seemingly naive question, which ends up being quite important to our story, is to say, how big is this symplectic manifold? I give you a symplectic manifold, you have to tell me how big it is. Give me a number. So what can we do to measure size? Well, one thing we can do is we can compute the volume of the manifold. I mean, I have a 2 form, I take its nth exterior power, I get a number. That's the volume. It's certainly a good size measurement. I mean, what might it mean to be a size measurement? Maybe the main point is that if I embed one symplectic manifold into another, a good size measurement had better have the property that it's no bigger for the thing I'm embedding than the target that I'm embedding it into, and that's certainly true of the volume. So pretty good. However, it certainly doesn't tell the whole story. So here I have a sphere packing, a ball packing, the famous cannonball ball packing. Let's compare to how symplectic ball packing works compared to this Euclidean ball packing. So one nice way that we can get a feel for the geometry of symplectic manifolds is by studying the symplectic ball packing numbers. So I can do this for any target, and I get a number, P sub k, which is just the proportion of the volume that can be filled by k equally sized symplectic balls. And so, okay, here's my computation for you of the packing numbers of the 4 ball. So, okay, if I have a 4 ball, I can certainly fill it fully with 1 ball. Now, if I want to put in 2 balls, it turns out I can get half the volume. That's a famous theorem due to Gromov called Gromov's 2-ball theorem. Okay, if I want to say put in 4 balls, I can again get all the ball volume. That's actually a nice thing to try to picture. It can be done rather explicitly from the toric geometry of the 4 balls. So you can try to work that out. And then things get a bit strange again. For example, if I want to put in 6 balls, I can get 24 out of 25th of the volume. And once I want to put in 9 or more balls, I can get all the volume. So you can see my caption here. Here we're packing some cannonballs in Euclidean space, but if you want to pack symplectic cannonballs in 4 dimensions, it's a much better story. If you have a box and you want to put in 23 4-dimensional symplectic cannonballs, you can do so. So these are rather mysterious numbers. For example, they're all rational numbers. They have a lot of properties. And whatever our theory of symplectic size measurements is, if it's a good theory, it should see some of this. So, any questions about anything I've I've said so far.
Any particular reason you wrote 20/25 instead of 4?
No, I mean, it comes at you a little bit more as 20/25. I mean, you'll notice that a lot of the denominators are squares, but you know, I can't say I gave it a huge amount of time. Okay, so yes, we'd like more symplectic size measurements. We have this volume, and it turns out that special to dimension 4, and I mean, I'm going to talk about this more at the very end with the open questions, but remember what I said at the beginning, we still don't really understand these symplectic Weyl laws so well, but in dimension 4, there actually are some nice size measurements that work well. Well, okay, so in general, it's helpful to think in terms of the following axiomatic framework. So what would it mean to have a good symplectic size measurement? Well, I should fix a dimension. And as I say, for the most part in this talk, we're really going to be interested in the case d = 2, i.e. dimension 4. But you know, we can do this in any dimension. And okay, so what do we want? We want to associate to every 2D dimensional symplectic manifold a non-negative real number, possibly infinity. And the case where the measurement is infinite will actually have content for us as well. And what should it mean to be a size measurement? Well, you know, it has this monotonicity property I said before. If I have one symplectic manifold and I embed it into another, then the size of the first is no more than the size of the second. It should scale reasonably. And to distinguish it from the volume, it's nice to guarantee that it is finite for the infinite cylinder. So this Zn of R is an infinite cylinder. I'll just draw it over here. It sits inside C to the n, which has a standard symplectic form. But as I said, I want to keep things at a fairly high level. The point is just that this infinite cylinder, if I looked at the volume, it would be infinite, but a symplectic size measurement should be finite for the infinite cylinder to show that it's really getting something symplectic. I mean, this is inspired by Gromov's famous non-squeezing theorem.
What's R standing for?
R is just the size of this.
Right. Okay.
So this is just a symplectic product of a two-dimensional disk cross R to the 2n minus 2. Okay, so these are what we're going to call symplectic capacities. And perhaps the first example was the so-called width, or the Gromov width, where if I have a symplectic manifold, I can just look at the largest ball that embeds into it. It's not at all obvious that this is actually finite for this infinite cylinder. You know, again, if volume was really telling the entire story, then that would mean that it should be infinite for this cylinder. But it's finite, and that's the famous Gromov non-squeezing theorem, and that's why this is called the Gromov width, and that's the appearance of the infinite cylinder in this non-triviality axiom. Okay, so this is our axiomatic framework for symplectic size measurements, these so-called symplectic capacities. And okay, so now I want you to revisit the Weyl law from this point of view. From this point of view, the question inspiring the Weyl law in symplectic geometry is rather natural. I have these fancy symplectic capacities that see things like the symplectic width of this cylinder. I also have the volume measurement. I would certainly like them to have some relationship to each other. And that's my question. Can symplectic capacities recover the volume measurement? So you might think we could do this quite a lot, but for the most part, we only have a really satisfying story in dimension 4, and okay, dimension 2 is its own, much simpler case. And so for that, I need to introduce these capacities. They're going to be linked to ideas of Morse called ECH capacities. So, you know, they're great. So let me try to convince you in a few bullet points that the ECH capacities are great. What would it mean to be great? So first of all, you should hopefully be able to compute them in some cases. Okay, So for the ball, you actually can compute them, and we're going to come back to this computation later. So I'm actually going to write it on the board. If I'm looking at the ECH capacities of the ball, they look like 0, then I have 2 1s, then I have 3 2s, etc. Okay, so already we actually learned something quite interesting about this from the point of view of the topic of the talk. Namely, we're interested in Weyl asymptotics here. So you can actually just check, especially if you're bored, combinatorially that this does see something like the volume of the ball, and you can check the growth rate, etc. Just from this computation. I mean, I have to tell you what the ECH capacities are, and I'll tell you what how to do this computation. But the numbers themselves are already quite nice.
Okay. You're going to tell us what K's indicate stands for.
Yeah, I will later tell you where the K comes from, but the point here is that K is just an integer. This is just a sequence of measurements.
So in the Weyl theorem picture, this would be like how many eigenvalues you have? Or...
Yeah, right. So we'll go back to the eigenvalue picture in a little bit, but this would be something like the different eigenvalues in some example counted with multiplicity, right? And we'll say more about how to define these and what K are. I mean, if you like the eigenvalue picture, imagine computing the eigenvalues for a cube, the Laplace eigenvalues for a cube. If you enumerate them, you'll get integer points in a circle, and you can prove the Weyl asymptotics by Gauss. I mean, a much simpler version of the Gauss circle problem. You know, you can really just prove it. It just says the number of lattice points in a circle approximates its area. If you look at this looks like the number of lattice points in an expanding triangle. So it's quite similar. Yeah.
My memory is the story is that Weyl was a student in Göttingen, and Hilbert, they asked the question in a drum, and they computed it for a circle and for a square, and then he went home and came back the next week with the general proof.
Right, that's along the lines of the story that I read too. And in fact, Weyl's proof gets you pretty far for proving the symplectic Weyl law from this example. If you think about Weyl's proof, it's, if anything, even easier to do for these capacities. Further questions? Well, I'm stopped. As I say, I like very much the give and take of drilling down because we have a mixed audience. It's good to know what people actually want to see. Okay, so you can actually compute them and you get something interesting. Also, not only are they measurements, they're good. So getting back to this ball packing problem, you could ask, when can I put a bunch of balls in a ball? Earlier, I did the case of equal sized balls, but you could also let the balls vary in size. And these, the ECH capacities, being capacities, will give you some obstruction to that problem. So the fact that this is a capacity means that if I have a symplectic embedding like this, the size of the left-hand side should be less than or equal to the size of the right-hand side. But the great fact about ECH is that it's actually sharp in dimension 4. So getting back to that somewhat mysterious looking table of ball packing numbers, that means that you can completely compute the ball packing numbers from these 2 bullet points. Okay, I have to tell you how to make sense of disjoint unions, but they just split on the algebraic level as a tensor product, and so there's a nice formula. And yes, you can just completely work out any simple example of a ball packing problem from these numbers and the sharp. So they're really telling us quite non-trivial information about the geometry of dimension 4. Okay, but of course this talk is called the Weyl law, or symplectic Weyl laws. So you might also hope that they recover the volume. Well, what's a good setting for that actually? These things, balls, etc. These are all examples of symplectic manifolds with boundary. In particular, they're examples of what are called Liouville domains. So Liouville domains are a very natural class of symplectic manifolds with boundary. So you should think of this, okay, so this is going to be some compact symplectic manifold. And I want it to have boundary, but in particular, I want the symplectic form to have a nice geometric relationship with the boundary. I don't just want, any boundary lying around to be a Lie domain. So one thing I can do is I could demand, for example, that the symplectic form is exact, and it restricts, the primitive restricts as a contact form. So I switched from beta to lambda, which was just a typo, but this is supposed to be, the symplectic form is exact, and its primitive actually restricts to the boundary as a contact form. We're going to need these contact forms again, so I'm going to write the definition of a contact form. So I have here like just a running list of things that we'll refer to later in the talk, because of course one problem with slides is that it's hard to go back. So being a contact form just implies that if I take lambda and wedge it with d lambda n times, I get a volume form. So these contact forms, they're like odd dimensional cousins of symplectic forms, and that's a Lie domain. As I said, please stop me if you have any questions. And okay, so now we can state the Weyl law. The Weyl law says that if I have one of these Lie domains and all its capacities are finite, that's something we need in order to have any hope of having something like this, then the ECH capacities do recover their volume in their asymptotic limit with square root of k growth. Are there questions about that?
Before, about definition of capacities, does one require additivity for disjoint sums?
Yeah, well, I'll give the definition in the next part of the talk, but for disjoint sums, well, they come from a algebraic invariant which splits as the tensor product, and what that means is that if I want to compute the kth capacity of a disjoint sum with n summons, I have to look at all the different ways of getting up to k and taking the maximum of those numbers. So I could write the formula, well, maybe I won't write the formula on the board, but for example, if I want to know the third capacity of the disjoint sum of two of these, I have to look at C0 of the first plus C3 of the second, C1 of the first plus C2 of the second, C2 of the first plus C1 of the second, and C3 of the first plus C0 of the second, and then just take the maximum possible way to do that. And that's not hard to see once I explain the construction. Further questions?
You go back to the theorem.
Yeah. Okay. More questions? Okay, well, we have many questions about how you actually define these ECH capacities, and it fits very well with the title of this event, this Morse 100 event, and even the title of my talk, From Morse Homology to Spectral Values. Okay, so let's think about Morse homology or Morse theory from the point of view of probably many people, but I actually learned about this particular details of this point of view from an article of Gromov's. Anyways, first though, let me advertise this nice picture of Marston Morse, who is also a faculty member at the Institute from 35 to 62. It's been great to be able to give a talk about this. So in the basic Morse setup, I have some kind of topological space, maybe a space of states or something like that, and I have an energy function on it, and I'm interested in the homotopically significant values where the topology changes irreversibly. So the kind of picture, I mean, this picture I actually learned about from Milner's book that people have is they have maybe a donut with its height function. This would be, say, the energy. And then you imagine I look at some sub-level sets. Here's E sub r, and I try to extract the values where the topology changes. Those are the homotopically significant ones, and those are going to be particularly of interest. And this point of view is a very good starting place for thinking about the construction of these ECH spectral invariants. Now, okay, as I said, Gromov has something to say about this too, which I like a lot. So actually, we can think of the Laplace spectrum from this point of view. Maybe you've seen this, or maybe you haven't seen this, but it's very nice. What you can do is if you have a Riemannian manifold, you can look at its Dirichlet energy. It's just the fraction of the L2 norm of the derivative divided by the L2 norm of the function. And this naturally lives on the projectivization of the space of functions on my manifold, which looks something like an RP infinity. Okay? So this is some kind of function on an RP infinity. And the Laplace eigenvalues are exactly the ones where the topology changes. And as Gromov points out, we can detect this even by looking at the following gadget, which will come up again and again in the talk. You can look at the homology of the sub-level set and look at where it would have gone, where it goes in the homology of the full space. So you can show that once I cross these significant values, I can't just go back down to where I started because the homology here is getting bigger and bigger. So anyways, if we want to connect with the work of Weyl, this is an important observation because it tells us that the Laplace eigenvalues also fit very nicely into this this game of finding homotopically significant values.
This is true both for compact M or for Dirichlet problem.
I think Gromov had in mind just compact M, but I think you can do something similar for the case with boundary. Any further questions? Okay, so to define the symplectic spectral values, we want to do this, but we want to do it in a little bit more of an algebraic way. I mean, Hellman in his introduction was talking about the work of Floor. I mean, already in this case, we see something that's infinite dimensional. In our case, things are going to be even kind of worse, topological spaces, and it turns out to be better to try to rephrase this in a more algebraic way. And then that ends up, Floor's observation is that that ends up giving a very beautiful story, which works pretty well. So how are we going to rephrase this in a more algebraic way? Well, there's a variant of Morse theory called Morse Homology, which is great and will be the prototype to everything that we want to do in this talk. Okay, so how does Morse homology work? Well, I still start with a smooth manifold. I still start with some kind of energy function, but I want to say that it's Morse. That means its critical points are non-degenerate, i.e. the Hessian is non-degenerate there, and I want to take a generic Riemannian metric. So that's my input, and my output is I can get a vector space that's independent of the choice of my function and my metric, and in fact, it actually computes the singular homology of the manifold. Okay, so that's a great thing. How do you make this thing? Okay. Well, again, we want to drill down on this a little bit because we're going to do this again and again, more or less. We're going to take the vector space freely generated by the critical points of the function. In this talk, we might as well always take our vector spaces to be over Z mod 2, because you can already get things very interesting there, and then you don't have to worry much about what it means, for example, to count things, because I'm just counting mod 2. And I get a map just by counting the flow lines from P to Q. Okay. Then the Morse homology is just the homology. I mean, if you know these terms, you would call this a chain complex, and this is the homology of this chain complex. But as I say, I want to put this in a rather high level point of view. Even just to draw for you some kind of example, a nice example to work through is just a circle. So here M is S1. I look at its height function. There's 4 critical points. Let's call them P, Q, R, and S. then the flow lines look like this. And I mean, I guess I'll leave it to you unless someone really wants to see it to actually work through that if you compute with this definition, you actually get the homology of the circle. Does anyone actually want me to do this? Okay, so that's great. That's our algebraic input. But remember that we actually want to extract numbers from this. This is just a vector space and we want to extract numbers. So to put it in Gromov's language, we want to find the topologically significant values from the Morse chain complex. That's the thing before I pass to homology. Okay, and there's actually a very beautiful way to do this. So it's quite a lot like the Milner picture that I drew before, but just more algebraic. So the complex actually has a filtration. Maybe just start with the construction part. I can look at the critical points that have value less than or equal to L, and that's a subcomplex. In other words, this differential maps it to itself because this is gradient flow. Okay, so I can take the homology of that subcomplex and it comes with maps into the full Morse complex. And so now if I have any non-zero class in the Morse complex, which is a topological invariant, I can just look at the minimum height required to represent it, and that will be a topologically significant value. That's called the spectral invariant associated to the class. Okay, so I want to pause because I mean this to be accessible, but at the same time, we want to do this construction again and again and again. So we definitely want to make sure we don't have any questions about what it is I'm saying here. Okay, so I claim this is a very powerful construction implemented in floor theory that gives you great things. All right, well, I don't hear any questions. I guess I wanted to advertise that this, this condition here, people didn't seem to object to it much. But remember, Gromov was already saying you can detect the topologically significant values by looking at this inclusion-induced map on the level of the topological space. This is just exactly the same thing, but it's more algebraic. Okay. All right. So now that was our warm-up. Now we're ready to go to floor theory. Okay. So remember, a funny thing is that many of the constructions that I say don't require anything about dimension, but we only get Weyl laws in dimensions 2, 3, and 4. I'll say a little bit about that when I can. Anyways, for this purposes, I'm going to have a three-manifold, but it will take a while for it to become at all apparent why it would be relevant that it's actually a three-manifold. It comes with one of these contact forms. And instead of looking at the Morse homology, we're going to look at the embedded contact homology, an invariant defined by Michael Hutchings. And in the spirit of connections with the Institute, let me advertise that he's the distinguished visiting professor here next year at IS. So I was going to originally put a picture of him, but I got scared because I couldn't find one in Creative Commons license. And then I was worried I would be like hauled off in chains in the middle of my talk. So anyways, but otherwise there would be a picture of him.
Glad you feel that way.
Let's advertise on Zoom, For all I know, there's like a lawyer taking a video. Okay, so we're going to keep things in a little bit of a impressionistic form, but I want to try to stay as close as possible to the analogy with Morse homology. Okay, so in the Morse case, we had a topological space and we had an energy function on it. In our case, our topological space is something like the loop space of our three-manifold. Namely, we want to look at the space of loops in here. And we want to define the energy to just be the integral of the contact form over the loop.
Do you have a baseband or?
No, my loops are just free.
Are there parameters?
That is a good question. I left it a little bit vague, but when we actually, because eventually we're just going to write down a chain complex anyways, and this is just going to be our inspiration. When we write down the chain complex, they'll be unparameterized. We're just going to look at the geometric image of the loops. Okay. Right. So as I say, we're gonna implement the Morse spectral value construction, but it is going to be a little bit subtle using this three-dimensionality in a subtle way. Okay, but we'll get there. All right. So what should be the replacement for the Morse chain complex? Well, remember that we were interested in the critical points of this functional. What are the critical points of this functional? The critical points are periodic orbits of this particular vector field called the Rabe vector field. So again, I have my running list of things here. Starting to become a little bit crowded, but anyways, I'll just keep the definition of the Rabe vector field on the board for you. If you want an example of interest that you can put your hands on, think about geodesic flows. If I have a Riemannian manifold, I can look at its unit, its norm one cotangent bundle. That will have a contact form such that the integral curves of the Rabe vector field project to geodesic segments. Okay, so that's what you can keep in your head. All right, so now we start to subtly use the word subtle. In the Morse case, I wanted just a single periodic orbit. Here I actually want sets of periodic orbits. And I also want certain sets that I didn't put on the slide. We'll see a little bit later why I make the choices that I pick. I don't mind saying, but there's a notion of elliptic versus hyperbolic orbit. And well, I want my set to be finite. And if I'm looking at a hyperbolic orbit, I don't want to include any of the multiple covers. But if I'm looking at an elliptic orbit, I do. So my only point there is to emphasize the word subtle. And to also emphasize dimension 3. Because you could also try this in a not subtle way in any dimension, and you do get something quite interesting, but it doesn't generally satisfy a Weyl law. So if you're interested in why one makes these choices, ask Michael Hutchings next year when he's here. Although you could also ask me. Okay. Are there any questions about that? All right. So this is our replacement for the Morse chain complex. And as I say, the critical points are these periodic orbits. Okay. What about the replacement for the differential? That's also very interesting. These are these so-called pseudo-holomorphic curves. Also, using a construction due to Gromov. This looks sort of out of the blue, but to try to motivate this to you a little bit, what if I tried to look at gradient flow of this functional? Okay, I mean, I'm on the loop space, so I could imagine that a flow line looks like a one-parameter family of loops. So that would give me something. If you work it out in the right framework, that gives you something that you would call a pseudo-holomorphic cylinder. Namely, I want, in this case, this would be a Riemann surface with two punctures, a twice punctured sphere, and I would be asymptotic to some Rabe orbit at one end and asymptotic to another Rabe orbit at another. So in other words, I have my contact manifold. I construct a symplectic manifold out of that by taking its product with the real numbers, and I study the solutions to this geometric partial differential equation, and they give me something that, at least in the cylinder case, looks like a flow line of the energy. And then, of course, in our case, everything is a little bit more subtle. So you want to not just require that your domain is a cylinder, you have to look at some rather complicated curves. So let me draw you a little picture again. Sorry, could you ask that again? I couldn't hear.
Is Earth answer Riemannian? To speak of pseudo.
Is the R cross Y an invariant?
Riemannian.
Riemannian, right. Sorry, yeah. So right. So I sort of I said this rather fast. All right, so Y comes with a contact form. That means that R cross Y comes with a symplectic form. Therefore, it has an almost complex structure. That's this J.
So you choose one.
You choose one, exactly. But the beautiful observation of Gromov is that you actually have a contractible family of choices. And so it's not dissimilar to how in the Morse case you had to choose a Riemannian metric to make sense of the flow line equation. It didn't depend on the choice of Riemannian metric. You have to choose an almost complex structure, and it's not going to depend on the choice of almost complex structure. Okay. So just to draw you a little picture, this is the sort of way one perhaps depicts a differential. Okay, I'm going to expand the slide in a moment, so you'll see a little bit more of that. What am I trying to draw here? I'm trying to draw some pseudo-holomorphic curve in Y cross R asymptotic to an ECH generator at plus infinity, which is some set of periodic orbits, and asymptotic to a different ECH generator at negative infinity, which is some other set of periodic orbits. And as you can see from the picture, the curves could have genus, they could have multiple components. It's subtle. They're not just cylinders, but this is the thing that works. Okay. Anyways, just to write this out a little bit more for you, my ECH generators are sets of orbits, and my linear map looks at all the other orbits and it counts mod 2 certain pseudo-holomorphic curves from one orbit set to another. And okay, well, at least we can say something now about why this is called embedded contact homology, and also give you some sense of why we're using dimension 3 rather than something else. Okay, so we want to make some requirement on these curves. Okay, well, in order to even do this count, we want them to lie in some zero-dimensional space when I quotient out by the appropriate relations, but there's something more subtle that we want. Namely, we want to actually say that they're embedded curves. And this is the first place in the talk where dimension 4 comes in some sort of interesting way. Because in dimension 4, you could imagine, this curve is some two-dimensional submanifold. It could intersect itself. It could have some nodal singularity or something like that. Those will live in the moduli space of pseudo-holomorphic curves, and they'll be robust phenomenon that I can't get out of by perturbing a little bit. However, I could just try to ignore those curves and say I just want the embedded ones. And that's a nice thing to do in dimension 4, but it's not a very good idea in higher dimensions because generically all the curves are embedded because you have some two-dimensional thing in a 6-manifold. So you get something quite interesting in dimension 4 this way. It's a little subtle how you set it up, but it's not clear what the proper generalization to higher dimensions should be, and it's not clear what the Weyl law should be in higher dimensions. Okay, are there any questions about that? Okay, so you can just take homology. That gives you this embedded contact homology. Now here comes something cool. Maybe it motivates for you why we had to make these rather subtle choices. In the Morse case, we got the singular homology of the manifold. What do we get in the ECH case? Well, Taubes has shown that you get the Seiberg-Witten-Floor cohomology of the manifold. So you get an interesting 3-manifold invariant this way. The Morse homology, of course, this makes sense for any manifold, the singular homology. Seiberg-Witten-Floor cohomology is a special invariant of 3 manifolds, and we don't know what the Seiberg-Witten-Floor cohomology of a 5-manifold should be. But the reason we made all these choices is that's what we get when we compute embedded contact homology this way. Okay, so are there any questions about that? So this is a very powerful isomorphism I mean, Taubes' isomorphism is now getting close to 20 years old, and in the intervening 20 years, it's sort of like somebody gave you, you know, a mammoth gargantuan tank, and then you won many wars or something. I mean, this is some extremely powerful tank that in the intervening 20 years, we've attacked, you know, problem after problem. For example, I won't put it on the slide, but a big open problem in symplectic geometry is the Weinstein conjecture, which says that there's at least one periodic orbit. The Weinstein conjecture immediately follows from this because the Symplectic homology is known to have infinite rank. So this immediately implies the three-dimensional Weinstein conjecture, which is still open in higher dimensions. Okay, so, all right, so that's the analog of this Morse homology. Now remember, we want the actual numbers. Earlier we called them the Morse spectrum. So now we want the actual numbers. We get the ECH spectrum. And this goes exactly like in the Morse case. Okay, so I'm going to go through it quickly because it's really exactly like in the Morse case. The differential decreases the action. I can look at the homology of the subcomplex. I can study this inclusion-induced map, and I can fix my favorite non-zero class here. Then I can look at the minimum height required to find it, and that's called the ECH spectral invariant associated to the class. So and
will this depend on J?
In principle, it could depend on J, but it turns out that it does not. You know, by some beauty. Again, analogously to, in principle, the Morse homology spectral invariants could depend on the metric, but it turns out that they don't. The main point is that you have continuation maps. So if I have two different J's, I can connect them with a family of J's, and I can find a map from one filtered chain complex to the other, counting curves for that parameter of J's. And that map also just decreases the action, but it can be inverted algebraically, and so you get independence of J that way. And again, I just want to advertise this construction and give it a name. I'm not sure it actually has a name anywhere, but anyways, I called it the filtered floor homology spectral invariant construction. And I put it in red because you can do this with any kind of one parameter family of floor homologies, and you get interesting numbers.
So in the Weyl context, of course, you were the spectrum of something.
Right.
Yeah, it will be or won't be.
Wonderful question. We don't know. Not obviously. That's what I mean, that it's more algebraic. They're in the Symplectic-Weyl case,
Yeah.
they look a little bit more like the spectrum of something, but even then they don't exactly look like the spectrum of something, and it's a wonderful question. In fact, I was giving a talk, and Leonid Poltarovich was in the audience, and someone asked that exact question, and I said the same thing, and he said something like, him and Helmut were talking about that in the 90s or something like that. So we only have this algebraic way of looking at it, not by the way, in the Laplace case, that would look sort of like the case of this where you have a perfect Morse function. You don't even have to worry about the flow lines, and so you just get the invariant on that. So that was also observed by Gromov. Okay. All right. So those are the spectral numbers. What about the capacities, the CK? That's what people wanted to know. Okay. Well, remember, for the CKs, we have a Liouville domain. That means that the symplectic form is exact and that its primitives, there at least I wrote, I fixed the typo there, its primitive restricts to a contact. So just to say straight away, we're only going to use the contact form. Namely, the definition of the CKs that I give don't depend on the filling of the boundary at all. They just depend on the boundary data. Okay, so as a warm-up case, it works particularly nicely when the boundary is a three-sphere topologically, which happens a lot. I mean, that's what happens when you have balls and things like that. It's quite a nice case. So again, I can just pretty much copy what works in the Laplace case with the Dirichlet energy. Namely, I have this inclusion-induced map you know, when L is like a negative number, this is just going to be empty. There are no orbits at all. When L is, you know, infinity, I'm going to get the full thing. So I just look at the values of L where the rank of the image of this map jumps, and I get a sequence of numbers, and those are the CKs in the case where the boundary is a 3-sphere. Okay. Are there any questions about that? Because earlier there were a lot of questions about what are these CKs and okay.
In principle, there is even more information. You can take one L, another L, and see.
That's right.
Is that any use? Or not?
Yeah, there's a whole theory of what are called barcodes that build on that. So you can get, instead of a spectral invariant, you can get a whole collection of barcodes. And these spectral invariants will look like infinite bars, but you get interesting finite bars, and those contain interesting information. There's actually a lot of information. I mean, there's work of some other authors detecting things like the entropy from the bars that you were mentioning. So, like I said, this is a very powerful construction that gives a lot of things, and we're just doing sort of.
Yes, usually when you have a filtered complex, you have a spectral sieve, but you know,
Yeah, there's other interesting things you can do there. I mean, maybe that angle is a little bit less explored, but certainly this idea of looking at L prime with L prime more than L and studying this thing has given rise to an entire theory of barcodes with a lot of implications.
So in this example, it's like the first value of L where there's a jump that jumps in rank by 1, and then it jumps in rank by 2.
In the ball example, that's right. Yeah. You have to be a little bit careful because even in the Morse case, I wanted a Morse function that meant the critical points are non-degenerate. The ball case is actually not Morse because the orbits come in families. You know, Morse ones are non-degenerate. I mean, if I have time, I actually say a little bit about how you do this in the ball case, but you want to perturb it a little bit. So that the orbits don't come in families. You want to perturb it to an ellipsoid, and then there'll be 2 orbits, one of action 1 and one of action 1 plus epsilon. What'll happen is you'll start at 0, then you'll cross the empty set of orbits, which has action 0. Then you'll cross the shorter orbit, which has action 1. You'll cross the larger orbit, which has action 1 plus epsilon, et cetera, et cetera. And the whole thing is continuous. So in the limit, you get these numbers, which is how you do it.
Isn't it surprising that just with the parameters of an ellipsoid, you could actually be enough deformations to get rid of the generic, however you want genericity? That's a bit surprising.
Yeah, yeah. I mean,
You only have a few parameters.
it's true, but it is enough. Yeah, I mean, even in higher dimensions, you can perturb to these higher dimensional ellipsoids.
It fixes all the higher Ks.
Yeah, yeah. You can get all the higher Ks just from this construction. Yeah, it is great.
I mean, for the boundary operator, you have to change the J2 to make it generic.
Right. Yeah, you have to bring the J along. That's helpful. Okay, so that works in the S3 case, and you know we have various things we want to say. So the general case is a bit worse, a bit harder. Maybe it's better actually, but anyways, it's a bit harder. So I'm just going to go through it a little bit just to give you a kind of impressionistic feel for it. So in the general case, I guess the main point I want you to get is that earlier we had spectral invariance for a single class. Now we want a sequence, so we need to just find some kind of sequence of preferred classes. And there's a nice way to do this because there's some additional algebraic structure on ECH, this so-called UMAP, which counts two-dimensional families of pseudo-homomorphic curves passing through a choice of marginal. So you get this wonderful structure, this UMAP. It decreases the grading. We didn't really talk much about the grading by 2, but anyways, there is also a canonical class, which is the class of the empty set. I can look at classes such that u to the k is equal to the empty set. I can take the minimum spectral value of such a class, and that gives me the numbers in the general case. And then these formulas I was talking about what happens for disjoint unions fall out from these 2 facts just algebraically. Okay, so now what? So we've covered some of our goals, but we want to do some of the rest. I did start about 5 minutes late, so I'm going to go until 12:05, but I promise I won't go beyond 12:05. Okay. So I have a few words on how to prove the ECH-Weyl law, a few in the spirit of finishing by 12:05. What were you going to say, Helmut?
Approved.
Yes, okay. The chair approves it. Thank you. Okay. So basically what I want to say is you have two methods, and they each have their advantages. Method one has the advantage that it's actually quite easy to understand, and it's quite analogous to what was actually done by Weyl in the 1911 paper. You can try to do it by just reducing to the case of balls by direct computation. So, well, actually, luckily, I already went through this with the question that was asked. So you perturb the ball a little bit to be an ellipsoid. You compute the orbits, just like I said. It turns out that this is another perfect Morse function case. The differential vanishes. The actions go exactly how you want. That means that the spectral invariants have to come as the action of something, and they have to come in order of action, for example, because they're detected by this U-map. And so that gives you the case of balls. This basically just says a little bit more about what I said when there was a question asked already. And so then you can actually just check that the Weyl law holds for the case of balls. Now, in the general case, you can try to reduce to the ball case just via a simple packing argument. Namely, I say you can try to reduce to the ball case. So this works, for example, for domains in R4. Well, what does it mean? Maybe I have some nice domain X. I have some nice domain X, which is sitting in R4. Okay, I want to prove the Weyl law for X. Well, I can fill X by balls up to an error of epsilon in the volume. So since I have limited time, you'll have to just picture in your head a slightly tighter ball packing. But I fill X with balls up to an error of epsilon in the volume. By the monotonicity axiom, that tells me if I try to run the ck squared over k computation for X, it's greater than or equal to the volume. And I can also put X in a ball and fill the complement with balls and run the Weyl law computation. And the same computation will then give me the matching upper bound. So it works very well. The only thing that doesn't work in general is you would need X to actually sit inside a ball, or at least inside something where you know that the Weyl law holds by direct computation. Okay, so hopefully that's rather accessible. Okay, but if you want to prove the full theorem, you have to actually use this Seiberg-Witten theory. This gets rather complicated, so we'll just be rather fast about it. We have this isomorphism of taubes that I was saying. Now this also is a filtered floor complex, so the Seiberg-Witten stuff has spectral invariance, but you actually get a family. In the taubes case, the whole point of taubes is to take the Seiberg-Witten equations and deform them in the direction of the contact form by a large deformation. So you get a choice, R, measuring how large you're deforming the equations. Okay, so I know we have a rather mixed audience here. I don't want to write out the Seiberg-Witten equations, but what I do want you to understand is that we have some system of PDE, and the normal case gives you the Seiberg-Witten equations, and Taubes' idea is something like to add to it R times a large multiple of the contact form. So in particular, we have this number R, so we get a whole family of spectral invariants. And the way we prove it is just by studying the asymptotics of the family. Taubes' idea in his work is that as R goes to infinity, the Seiberg-Witten floor homology should limit to the embedded contact homology. And the version of that for us is that our whole family of spectral invariants limits to the ECH spectral invariant. Okay. On the other hand, we also show that as I vary R, the spectral invariant actually doesn't change all that much. Okay. So that's helpful because on the other end of the asymptotics, when R is small, you can more or less actually just solve the Seiberg-Witten equations exactly. you get what are called the reducible solutions, and they have almost a closed form, and you can actually just compute this. And what you get is you get the following even more general Weyl law called the contact Weyl law, which says that if I have any sequence of classes, there's a grading on them. For time reasons, I didn't have much time to define the grading, but it is the thing that has the property that the differential decreases the grading by 1. And it tells you that I can always recover the contact volume from the action of the classes divided by the grading. So this is more general than the ECH Weyl law, the Weyl law for the ECH capacities. It implies it because in that case, the classes all were related by this UMAP, which decreases the grading by 2, but it works for any sequence of classes. And it's also just much more natural from what you would get with the Seiberg-Witten theory. It in particular emphasizes the UMAP has no real role in the Weyl law at all. It's just used in defining the capacities in the first place. Incidentally, this UMAP is itself an interesting thing, because much earlier we were seeing the cohomology of RP infinity in the Laplace case, and the UMAP is playing something like a role analogous to a generator of the cohomology of RP infinity. But it's not really relevant for the Weyl law. Yeah.
The Seiberg-Witten homology doesn't depend on the contact form.
That's right. It's again like the Morse case. The homology doesn't, but the contact form gives a filtration, and then the filtration, does depend on the contact form. Yeah. So these are technically parameters of the contact form and R. Do you have further questions? Okay. Well, we should move on because people want to eat. Okay, so applications. Well, luckily we can do this quite fast. Also, Solon is going to talk about some things that are applications as well. So anyways, we'll go through this fast, but I just want to say the point. Okay, so Smale's 10th problem asks, are periodic points dense in the non-wandering set for generic CR diffeomorphism? The regularity here is important in Smale's question because for R equals 0 or 1, these are along the lines of what you would call Pugh's closing lemmas. But we want to know in higher regularity whether you can get this to work. And Smale singles this out as one of the main problems to think about for the 21st century. So the main point I want to make is you can get great results about the closing lemma using these spectral invariant Weyl laws, as was pioneered by a wonderful theorem of Irier, which says that in C infinity, so this implies the CR case for any R. In any R, a generic contact form has a dense set of periodic orbits. So the reason this is called the closing lemma is because you imagine that you have an open set and you want to perturb in a C infinity small way to get a periodic orbit to pass through that open set. Okay.
Sorry, what is generic?
Yeah, generic in the bare sense. It's topologically generic. So, okay, we'll just say the proof is actually very short. Irier's paper is about 5 pages or something. So we can almost do it, but we'll go even faster through it. The crux of the issue is I have an open set. I want to make a small perturbation to the contact form that gives a periodic orbit going through the open set. So what do? I scale up the contact form supported in the open set. The Weyl law says that one of the ECH spectral invariants had to change because the volume certainly changed. And the flow is exactly the same outside of the open set because I scaled it inside the set. So if there were no orbits that arose going through the open set during that perturbation, the spectral invariant would be exactly the same. So that's more or less the proof. Okay. So the upshot is these Weyl laws give fantastic results about closing lemmas because they allow you to detect something local like a periodic orbit passing through U by something global like the volume. Okay. Now I will just briefly say that you can find more Weyl laws for surfaces, and these have also been very powerful. So there's essentially 2 ways to do this. I just want to highlight the first, really. Now, if you have a surface with an area preserving map, you can still do this to get new spectral invariants which actually see the map. And the main point is you can just look at the mapping torus of the map. That's also a three-manifold. And you can just run the construction and you get invariants of the map, these so-called periodic floor homology spectral invariants. Those also satisfy a Weyl law, and using that, you can prove an even better closing lemma. I mean, okay, maybe it's not better, but probably more exciting, because it's just a closing lemma for a general area-preserving surface diffeomorphism, which is a very natural case. Maybe the contact case could feel a bit special. So you can prove a Weyl law for just a general area-preserving surface diffeomorphism by doing similar kinds of things to the mapping torus. Of course, the Weyl law is quite hard. It took a long time to get this to work, but it does work. You can also look at this three-manifold from the point of view of its Haggard floor homology. You get an interesting story, but I'm gonna just mostly skip that. I guess I'll just say in Haggard floor homology, you want to look at the symmetric product of the surface and try to find interesting Lagrangians. So you could, again, take your surface. These red circles give you Lagrangians in your surface, and you can get interesting Lagrangians by looking, say, at this one in the fourfold symmetric product. You can again run the filtered floor homology construction, and you get other interesting spectral invariants that we call the link spectral invariants. And Solban is going to use one or the other of these invariants. I mean, you actually just need either the PFH ones or the link spectral invariants for what Solban's going to say. Okay, so I have 1 minute left, and I have two questions. Here are what I think are the million-dollar questions about this. What happens in higher dimensions? And in some sense, that's probably the more interesting one. But also very interesting to me is what about the subleading asymptotics? So we already discussed higher dimensions. For the subleading asymptotics, you know, Weyl's original law, they've had 100 years head start on us, and they do have some results, but still actually some mysteries in the subleading case. And we have some conjectures too, recovering something like Weyl invariant. There have been some applications. There have been some results, but it's still you know, quite mysterious. So I'll stop there as promised. Thank you.
Thank you much for this wonderful talk. So, other questions, Peter?
In fact, you have a next term? I mean, do you have a little, do you have a rate?
Well, we don't quite know, but yeah, actually, I mean, very recently, at least in the periodic floor homology case, Oliver Ettmeyer showed that you do have O of 1 growth in the periodic floor homology case. In the ECH case, Nikhil and I showed that you get something like k to the 1/4 bound, but it's probably O of 1. And Oliver showed that, you know, at least in the case of domains in R4 in the ECH case, you do have O of 1 growth. And earlier Solban and I showed, you know, some other O of 1 growth type of things. It seems to be connected to the algebra of the group of Hamiltonian diffeomorphisms, which is itself quite interesting. Theorems of Ben-Yaga about simplicity, which will come up in.
Maybe you know that or not, that Hermann Weyl himself said, I have a conjecture, but I don't want to make it public because he was so nervous about the boundary being the next term.
I see. Yeah, you can certainly compute the subleading asymptotics in this case, and you get the affine perimeter of that triangle. And you also have a story like that for any toric domain that has recently been worked out.
Tim, more question? Okay, so let's thank our speaker again.